Okie dokie. Today we're going to go through something called Feynman's electromagnetic mass of the electric field surrounding an electron. You can find this in Volume 2 of his Feynman's Lectures on Physics, Volume 2. It's the one that says mainly on electromagnetic phenomena. On page 28-1, it was published in 1964. That's the Feynman Lectures on Physics, the famous lectures that he did for Caltech. It turns out that actually the first time I saw it, though, was in this... not that I'm this old, but I have old physics books. A physics book called Principles of Modern Physics by A.P. French, published in 1958. On pages 63, 64, 65, 66, and 67, he did it about 6 years earlier than Feynman when he published them. Although I don't know, that's when Feynman published it, and that's when this guy published it, who I assume probably this A.P. French did it first, but there may be others. I don't have every single physics book ever written, so I'm just mentioning these two sources as sources of this lecture, and also for you to go and look it up for yourself. Because I'm not going to give all the details. This would be a humongous lecture. It's going to be long as it is, and I'm going to move pretty fast through it. So there are some details that are missing, especially pictures and whatever. So let's get started here. What we're going to do is figure out the energy of the static electric field that's surrounding the electron. So it's external of the electron. It's not inside the electron. And I have another lecture on we do the electric field inside the electron. This is figuring out the electric field from the edge of the electron out to infinity, what the effective mass of that would be. So if you look at my other lecture, I tell you that the total electric energy is equal to the electric energy density, the integral of the electric energy density times the differential volume, of course. And we'll do the integral from A, the radius of the electron, to infinity, out to forever, because the electric field will go out from the electron infinitely. And the electric energy density, of course, is 1/2 epsilon naught electric field squared of the electron. Epsilon naught is 8.85 times 10 to the minus 12, just to give you that constant. So this becomes this because energy density is 1/2 epsilon naught electric field squared. Here's the 1/2, here's the epsilon naught. Electric field of just a single charge electron is K naught Q divided by the radius squared. And of course it's the electric field squared, so there's the squared right there. The differential volume, we'll assume it's a sphere, so it's 4 pi r squared dr. So let's see how this becomes this. Here's the 1/2. 4 pi epsilon naught on the top is K naught on the bottom. If you like, I can write K naught for that. I did the algebra already, but I'll do it out for you again. So 4 pi epsilon naught is this K naught, and then you've got K naught squared on top, so this will be squared. So this will cancel with one of these and leave 1 K naught, which is the algebra that I already did for you before. Here's r squared squared, but it's on the bottom, so that's r to the 4 on the bottom. R squared on top is 1 over r squared. The integral of 1 over r squared, of course, is negative 1 over r from a to infinity. From a to infinity, stick in infinity, you get 0. Minus negative is a positive. 1 over, stick in a, 1 over a. So there's the 1 over a right there, okay? And there's the q squared. I don't know if I mentioned that already, okay? So everybody here, if you do this integral, is right here. All right. So this is the total electric energy of the electric field that goes out from an electron. So if this is an electron right here, this is the electric field that goes out to infinity outside of the electron. And if you have the total energy, of course, Einstein said that the mass is equal to the total energy, all of these people, divided by c squared, because energy equals mass times c squared. So mass equals energy divided by c squared. So the mass effective is this, the total energy is this. This divided by c squared is the mass according to Einstein. Okay, that's one way to figure out the electric field outside of the electron, the total, the effective mass of the electric field that surrounds the electron from its radius out to infinity. What we're going to do next is figure out the momentum of the electromagnetic field. So here we only dealt with the electric field. Here we're going to be dealing with the electric and the magnetic field that surrounds a moving electron. Here the electron was just static. It had a velocity equal to 0. Here our electron will be moving. That's why we're going to figure out the momentum of this electromagnetic field. And then we're going to figure out the effective mass of this electromagnetic field also. But let's get started with this. The total momentum is equal to G, we physicists call the momentum density. And since it's density, of course, you're going to want to do the integral dV just like you did before. So this is in momentum divided by volume times dV will give you momentum right here. So momentum equals momentum density times the differential volume, the integral from a to infinity again. The momentum density is equal to, or the magnitude of it, is equal to epsilon naught E cross B, the electric field crossed with the magnetic field, just the length of that vector. And here's the epsilon naught. The length of the vector is magnitude of E, magnitude of B, times the sine of theta. Okie dokie. I know I haven't dealt with the dV. We'll deal with that later on in just a second. This is going to be quite a bit bigger integral than this one was. The magnitude of the cross product is EB sine theta. What we're going to do is we're going to get it into only either the E or the B. I've decided to change everybody into the E field. So I'm going to get rid of this B field right here, the magnetic field. B field is electric field divided by C. And that equals, but we're going to have this thing's not going to be moving at the speed of light. We're just going to have to be moving at near, not even near the speed of light. We're going to have moving very much smaller than the speed of light. So what we can do is we can take this equation. If we want a little magnetic field, it won't be E over C. It will be, we'll take this equation and multiply it by V over C. That will be unit neutral, so it won't change the units on this thing. And so now we'll get EV over C squared right here for Mr. B. So Mr. B right here is EV C squared. So if you stick this into here, you'll get E squared V C squared. E squared V C squared. So these two people right here become all of these people right here. And there's the epsilon naught, there's the sine theta, there's the dV. Now, it turns out, I'm not going to go into it that much because we're here just to basically do the mathematics, and these are the details you can look up when you, if you look at these up in the books, you can look up the details. But what we want is, because of the flow of the movement, the velocity of the electron, we're going to want to have the sign component of the momentum density. So we'll have G sine theta. We'll have to add. So this really won't be G. It'll be actually G sine theta. So we're going to have to add another sign here. So there was a sign because of the cross product, and now I put this little s right here, and that s is actually another sign. So we have two signs that are multiplied, sine theta multiplied, and it gets worse than that in just a second. Okay, we went right here and did all this. We're going to come up here. Here's the epsilon naught. Here's the V. Here's the C squared right there. We need the electric field. I already told you what the electric field was right here of a single charge is K naught Q over R squared. There's your K naught Q over R squared right here. I'm using a little r because we need a big R for a different reason. So I'm actually going to use a little r here. So K naught Q over R squared, just like it was right over here for the electric field here, for the electric field right there. The C squared is right there. There's a 2 sine thetas. Here's the 2 sine thetas, and then the dV. Now we're going to finally figure out what the differential volume element is. And here's our electron moving with a velocity this way towards the right. It has a little r, this is little r, and a little angle d theta right here. And what we want is this ring right here. We want the differential volume element of this ring. So obviously if this is d theta, the thickness here will be r d theta. And the thickness of the ring will be a little bit of the R component right here. So it'll be just dr. So this tire will be r d theta thick and dr wide. And we'll need to know how long it is around. Well, that's a circumference, so we'll need the radius, and this is why I use little r. If this is theta right here, and this is little r, then this side right here, of course, is little r sine theta is this side right here. So I'm going to call that big R. I hope that doesn't confuse you guys. But this is big R right here, whereas this is little r right here. So how long is the circumference, of course? Well, the circumference around is 2 pi times big R, little r sine theta. So 2 pi little r sine theta is how long it is around. That's this dimension. This is dV is a 3-dimensional object. So the dimension, circumference dimension is right here. The height dimension is r d theta, which is right here, r d theta. And then the thickness dimension is dr right here. So what's dV? dV is 2 pi little r sine theta r dr d theta. This is going to be a double integral. Okie dokie, we're done with this page. Let's go on to page 2, which is right here. Alrighty. So, as we had before, if you're writing this down, you'll see that in your notes you've got epsilon naught v c squared. We had that over there. K naught squared q squared r to the 4th is over there too. We have actually 3 sine thetas. We have 2 sine thetas before, and then when we did the dv, we had another sine theta. So that's 1, 2, 3, which is sine cubed. So this is sine cubed right here. So we'll have to do the integral. This is a d theta. The integral of sine cubed d theta, which turns out to be 4/3. I'm sorry, from 0 to pi, because we'll be doing it. Theta will go from here all the way to here, from 0 to pi. And if you do sine cubed d theta, sine cubed theta d theta from 0 to pi, I promise you'll get 4/3. All right. So we did the sine theta integral. The other integral will be the r integral, and the r integral, of course, is r squared. R to the 4th on the bottom is again 1 over r squared, and the integral of 1 over r squared equals negative 1 over r, and we'll have to go from a to infinity, just like we did before. And so what we got before was we got 1 over a right here. Okay, so I'm sorry. From here to here we have the 4/3. I'll just do this, and then I did the integral here, the r integral here, which will give you the 1 over a right here that we're getting from here. So I'll make sure everybody's here. This there's the epsilon naught, there's the pi from right there, the v, the c squared. All of these people are sitting here when the r to the fourth and r squared cancel. Here's the 4/3 from the sine cubed integral, and then there's this 2 right here, will be right here. Okay? So I think everybody here is here. Now we'll do the integral of 1 over r squared, which I told you, just like before, turns into 1 over a when you do that integral. 1 over a. So we have these people, we have those people, we have the pi. I think we lost the pi. There's the pi. So there's the pi, there's the v, there's the c squared, epsilon naught, k naught squared, q squared. The 1 over a is the integral of 1 over r squared. Here's the 2 right there, and here's the 4/3 right here. All right? So everybody here is here, although I did forget to, I'm dragging so many people, I forgot to bring Mr. Pi. So there's the pi, I wrote him right there. Made a little mistake. Okay, we're going to need to do a little bit of algebra on this. Let's see what we can do. Alright. Alright, so epsilon naught, v naught, v is here, c squared, pi is here, k naught squared, q squared, 2a, 4/3. Actually, I don't think I did anything here. What I did here was, I'm sorry, I have it right here. I changed this is the momentum, which is what we said before. I changed the momentum to the effective mass times the velocity. So I didn't change anything here. I dragged everybody over. It looks like I changed stuff, but I didn't. I just changed this here. And if we solve for mass effective, we'll have to divide by v, so these v's will cancel. And here I did do a little bit of work. The 4 pi epsilon naught is k naught on the bottom. So if you want, I can write k naught if you want here. Then you'll have the k naught squared here, and so this k naught will cancel with one of those, so you'll be left with the k naught here. Here's the q squared, here's the a, the 2/3 is in front here, and remember I have the 4 pi epsilon naught is this guy right, was this guy right here. And so that. So if you do a little bit of algebra here, you'll get this. And I also divided by v, so the v is canceled. So we get an effective mass of this. All right? Now, how is this effective mass? That's the electric and magnetic. This is the effective mass of the electric and magnetic field of an electron that's moving slow compared to the speed of light. How does that 2/3 these people compared to what we got before with a static one and only electric? Before it was 1/2 the same people. 1/2 k naught q squared a c squared. Here now it's 2/3 k naught q squared a over c squared. So all of these are the same. K naught q squared a over c squared, k naught q squared a over c squared. Those are the same. It's just the front people that have changed. It's changed from 1/2 for only the electric field and not moving to 2/3 for electric and magnetic, and it's moving. One last thing we can do with this is I wonder if it's moving near the speed of light, what will the effective mass be? Well, of course, we'll just add, it still has everybody in there. There's the 2/3. There's the 2/3. Here's these people right here. And here's these people right here. And we'll have to add this factor right here. Of course, the Lorentz factor of 1 over the square root of 1 minus v squared over c squared, the special relativity factor that we have. I'm sorry if that was not in the, hopefully that's in the viewing screen. I'm trying to do that, yeah. So mass effective is 2/3 k naught q squared a over c squared, square root of 1 minus v squared over c squared right there. K naught, again, is 9 times 10 to the 9. The charge on the electron is 1.6 times 10 to the minus 19 coulombs. The radius we would not know, but we know the mass of the electron we do know, so we can solve for the radius again. Speed of light is 3 times 10 to the 8th. This velocity would be arbitrary. It's whatever you'd like to do at this. and the speed of light squared again here. So this is if you're going at low velocities, and this is if you're going at velocities near the speed of light. All right, 20 minutes. Hope you enjoyed this lecture, and I look forward to any comments at the bottom. Thank you very much.